today I'm going to some problems, some results, which are part of the work in progress with Nina Uraltsova. And it's, of my point of view, a quite nice problem. And it looks like as follows. We have a question, and on the left-hand side, it's a standard heat equation. And on the right-hand side, we have some operator. I define it a few minutes later. And this operator is just called hysteresis. And we have a question, we have, of course, some initial conditions, and we have some kind of boundary conditions. I would be not specify this condition, so there is something. And it's interesting, this hysteresis operator is in general a multivalued. So how we can define the value of this operator for U? So we have two thresholds, alpha and beta, and we assume that alpha is less than beta. And then if our U, how we define the hysteresis operator? I would like either of you.
It is not operated. Multivalued is function.
Okay, that it would be function. Okay, if you would like F, okay, let's it would be F.
Okay, just
We change it.
Otherwise, we will not proceed.
Operator is uniquely defined. Function is multivalued.
I just would like to define operator. Okay, if you would like, so we consider such a function. Function F. Function F. And how we define this function F? If S is less or equal than alpha, then this function takes value -1. If S is bigger or equal beta, this function takes value 1. And what's happened if S lies between alpha and beta, then this function is +1 or -1. Okay. And now I just draw some picture. This is 1, this is -1. Okay. And how to define the value of this hysteresis operator independent of U? First of all, I have initial condition. I know this function. So I assume that is given. So here is the value of U for all such points. If U is less or equal than alpha, then our hysteresis operator gives us -1. If U is bigger or equal beta, then here I get +1. And you can see here is -1, here is +1. And if U is between alpha and beta, then our hysteresis operator takes the same value as it was before. How we can define it? We have a point x on t such that the value of u at that point lies in this interval. And after that, we just goes down so on this straight line, on t, unless we first time we met some point tau such that x on tau satisfy so that u from x tau is less or equal alpha, and then we have -1, or u from x tau is bigger better than +1. Of course, that can happen that we just go to our initial condition. But here we know +1 or -1 we have here. This is given, this distribution. What is essential here for this problem? So if we come here, that the jumps from -1 till 1, it's possible only on these thresholds, only if u is equal beta. If we jump from +1 to -1, it's just possible on these thresholds. So that means that we can have several travels along this loop, and maybe sometimes goes away or still continues. This.
So this force of jumping up or down or going from -1 to 1, it comes actually from the initial data.
Yes.
Okay, so you don't know that.
Yes. But it's given, so we know this. Originally, such problem, as example of such problem, we can consider. So originally, we can consider some biological problem. So we have salmonella, and we have some plate with a jelly. If we have enough such jelly, salmonella have enough food, quite happy, and the density of its population is growing. But suppose that we have such amount, some constant amount of food, so that means that population is growing, and after some time, we have too many bacteria and less amount of the food. It's not enough for all, so the growing should stop. And it's just go down unless the amount of the density of this bacteria again reach these thresholds. And after that, it depends on some additional conditions, so that means the population can growing and the population can still become less, and all bacteria died. The second example, which is probably it's even more clear, is the so-called heating cooling. So if weather is not so terrible as outside, so we made our heater on, and our temperature increase until certain level. After this, heater is off and cooling system is on. And it works unless the temperature just rise this level alpha, and again and again. It's also some possible example to consider some population dynamic. Suppose we have some region with a good payable job. So people just come to this region and the rent price is growing. But it's until the market is full, so we just reach some critical level. And after that, some crisis, loss of the job, people just move away and the rental price goes down. In fact, it's such a problem can describe a lot of processes where we have several substances, and these substances interact each other according to such hysteretic law. There are many problems. And what some special things which correspond to this problem? What I would like to emphasize. So, first of all, our right-hand side is multivalued. The second point, our right-hand side is not monotone in U. And here it's a difference between this problem and the well-studied two-phase problem, two-phase parabolic problem. And I just recall that such a monotony on the right-hand side in two-phase problem was quite essential in studying the optimal regularity of solutions, the regularity properties of the free boundary. Here, it's not such a case. And the third point, that we have some kind of directed jump. So this means that jump from -1 to +1 is possible only on the line u equal beta, and the vice versa jump from +1 to -1, it's just on the level set or equal alpha. And since we have a jumps, so it should be some kind of free boundaries. So, and free boundaries in this problem also looks like a little bit different from previous problem of such types. So how we define these free boundaries? First of all, let us define two sets, omega plus and omega minus. So it would be all points where our heat equation is equal +1 or -1. And then the free boundary we define as a set of points where we have change of our phases. So where we have jumps on the right-hand side.
Let me just ask something or you want to comment? So you assume just that h has a discrete value.
Yeah.
So this is just ±1.
Yes.
So there is a. Could you allow it to be also continuous, but you don't know what it is? Just switch on. You just switch on and off. That's all.
If it's not switch, okay, you see that.
No, no,
That's
no.
also possible. You just sit on this line for all time. So it's not forbidden, but it's not interesting.
No, my question was where you could have h could have different values all the way between -1 and 1.
Of course, Henrik, of course. It's possible to consider, so it's the simplest case. Of course, you can consider not this -1 and +1, you can consider some functions here.
No, yeah,
But it would be,
only on this
Only on these two level sets.
Which we don't know what it is. That's okay.
So, and how we define this? So this is the sets where we have a jump. But what kind of problem we may expect? Okay, first of all, some remark. Alpha is less than beta. So then these two sets are separated from each other. It's clear. Due to the definition,
But then you are assuming that U is continuous on one side.
U is the following. Our right-hand side is bounded.
Well, I mean, in order to consider the sets U equals A, you assume that they are not
Okay,
almost everywhere.
let's see. Here we have such an equation
Yeah, but U
with
is
bounded right-hand side.
My
So
question
that
is-
means that U should be from W to 1Q.
Okay,
So that's immediately.
thank you.
For all Q with an infinity. So it's automatically. By this reason, we can consider this. Okay. What we can also, what kind of gamma we define then the following subsets. That gamma from U, which is intersect with this set, we denote this as gamma alpha. Gamma from U, which intersects with another one, we denote as gamma beta. Since we have no intersections from both these two parts, so it's enough to study just one, for instance, gamma alpha or gamma beta, and just understand that for the rest, we can get the similar results using the same arguments. And from the definition, it's clear that gamma alpha and gamma beta are graphs. But what we can have here? Okay, let's it would be just t direction. And it would be gamma alpha. So that means if I have gamma alpha, that means that I have just jumped from +1 to -1. So that means that below I should have omega plus and above omega minus. No, picture is not good. I just change it a little bit.
Why is gamma alpha a curve?
What?
Why is gamma alpha a curve?
A curve?
It's a graph.
It's a graph.
Why?
What you
So it's just by definition. So what is gamma is a set where we have this change of these sets. And these two sets are separated from each other. And if I go in t direction, I can intersect just in one point. So it would be graph. Okay, maybe just such a picture. Okay. Yes, it would be this one. And this is gamma alpha. Below I have omega plus. Here I have omega minus.
So that's not a curve.
Just a moment. Just a moment. Just a moment. Exactly. So it should be the set U is equal alpha. And it should be graph. as you remark. But that can happen that not the whole level set U is equal alpha is an element from free boundary.
Не туда, вертикаль, справа.
Какую
Там, где
вертикаль?
U равно альфа, там надо выстроить вертикаль, когда она загнулась налево.
Вот здесь вот.
Отсюда наверх.
Подождите, где моя картинка? Да все нормально, мы до сих пор ее рисовали. It's here. Да, не туда загнулся. Okay. Third iteration. Okay, omega plus, omega minus, and then here. So it means that this part of the curve is not an element of the free boundary. Because if it's a free boundary, that here we should again have omega plus. But such a jump from omega minus to omega plus is possible only if U is equal beta. But here we have just U equal alpha. So that means that for our free boundary, we may...
So this is not a possible picture, that's what you're saying.
Yes, yes. So that means that it should be some vertical part of, it's not excluded, at least. If we have such a strange behavior of the level set, then it should come such a vertical part.
Okay, let's see, what you're saying is if you start in omega minus, when you use alpha, you go up and hit the point.
If I start from omega minus, then for free boundary, it should be next, it should be omega plus. And that's happened just for U is equal beta. So that means that if we have, so if some gamma, omega plus, omega
So
minus,
it's a graph.
so it's gamma alpha, so that means the next should be gamma beta. And such a turn, it's not possible.
With vertical, omega minus is a graph.
But I mean, you can have situation where you cross the alpha level from this side to this side. So this is possible, but this is not free boundary, right?
So that means if we are here, on this, so we just cross the alpha, but we are still on this,
Yes, yes.
we have no jumps. So it's a level set, but not free boundary.
So the picture is possible, but
Picture is possible, but so the picture is possible, but free boundary, it's just this,
yeah.
but not something,
I'm sorry, why is that part not free boundary?
which one?
The upper bar.
This one.
Yes. Why is that not a free boundary?
Because this is level.
It's the level set, U is equal alpha.
Yes, but you are still, if you go from that part up, you are again going from U plus to U minus, right?
Yes, but it should be graph.
It is U minus.
It's U minus. It's U minus. It's again. It's still again U minus. So we have no change. Okay, omega minus here, omega minus here. So if it would be free boundaries, it should be U is equal beta.
Yes.
Not the case.
Sure, okay, sorry.
Good. So what parts of the free boundary we can have? So we can have this vertical part, gamma vertical, and then we also can separate the rest of this for two subsets. So we can define the subset gamma 0, alpha or beta, and gamma star, alpha or beta. So gamma 0 we define all, okay, I just define what is gamma alpha 0. It's just all point which belongs to gamma alpha, such that gradient u are 0. And gamma star we define as gamma alpha minus gamma 0 alpha. And the final aim is just study regularity of this gamma alpha 0, gamma beta 0, gamma 0, gamma star on gamma vertical. Okay, with vertical part, with regularity, all is clear. And consider separately these two sets. So what we have for gamma star? Observe that on gamma star, by definition, we have that gradient of u is positive. The absolute value is positive. It's not 0. So we can apply the implicit function theorem. And then immediately get the gamma star is regular. Yeah. Okay. What's more? It's a first. What is the second? Second, we can show that the time derivative is continuous across gamma star. It's some job, but it's possible to do using von Mises transform. And von Mises transform and this LQ estimate. Okay, time derivative is continuous across gamma star. Now, let's consider gamma star beta. What we have here? Here we have omega minus, here omega plus. And we just go in t direction. So what we see? We see it's clear that it's not difficult to see that on gamma beta star, we have the estimates that ut is not negative. If now we consider gamma alpha star, so here we have omega plus, here omega minus, and again we just go in this direction. What we can see? That we can see that ut is less than or equal 0. And what is also possible to show that there is some constant, and this constant depends on the maximum of our solution. So I just add here that we assume and this estimate is true locally near gamma beta star. So we have non-negativity exactly on gamma star, and we have some estimates, one-sided estimates from above near gamma beta star. And the same story near gamma alpha star. So we also have some kind of one-sided estimate here. And it's again locally near. And now let's summarize what we get for gamma star. We just get
The intersection is when there's a line, yeah?
what?
The intersection of them, there should be a line.
Intersection for what? The
Gamma star beta, gamma star alpha. Is
no intersections. Gamma star beta and gamma star alpha, it's some separated. No intersection at all. So we just estimate for UT on gamma star. So we can estimate time derivative there. Okay. And now let's move to gamma 0. And ну потом. Давайте потом.
So this point where you have this vertical line
Yes.
is part of gamma star.
Gamma vertical?
This point which you have on this picture
Yeah.
is part of gamma star.
No.
So the gradient,
No, it's not a part of gamma star.
so the gradient there is 0.
No. On gamma star, our gradient with respect to x is non-negative,
Non-zero.
non-zero. It's non-zero.
So at this point,
And that point we just go, so it's just fixed x. And this is a vertical part. It's parallel t.
But it is not level set for you. It is
I
not
know,
alpha
but this,
or
but
beta.
this point is part of the level set.
Which point you mean? You mean this point?
Yeah. This point, yeah.
Okay, and what we have here? That u is equal alpha here, u is equal alpha here. And what is in between?
Well, I can see whether the gradient with respect to x
You
vanishes or
can
not.
say nothing. It may be 0.
It's maybe zero.
So it may be part of gamma star, but then,
Yes.
It's maybe, but it's not necessary.
but then you can't apply the implicit function theorem at that point.
But you see, on this gamma star, we just would like to study the regularity of this. And this is...
Окончательный результат будет ясно, что вот вертикаль вообще не приближается.
Да ну,
Вопрос связан с этим.
Нина Николаевна, вы будете меня все время забивать? Я сама
I
сажусь.
suggest her to claim the main result. Then outside gamma vertical, we have proved that the following.
We have proved the following outside.
Vertical.
Since Nina Nikolaevna would like to have result immediately, I formulate the result. Just for you. Okay, so let our function, z0 would be a point of a set where we have our problem, and it would be such a point that the parabolic distance to the gamma vertical would be positive. So we are on some distance of this, this gamma vertical. In this case, we can estimate the second derivative with respect to x and the first derivative with respect to u via some constant, which would be depends on the maximum modulo of solutions and this distance rho 0. This is our aim. So what we would like to get. And such estimates, it's some crucial step for further study the regularity of the free boundary. We need it in order to apply some rescaling, some blow up in the future.
Is it one space dimension?
No, it's multi-space dimensional. So in fact, your question is good. So that means that originally, then this problem was first formulated by a person who studied hysteresis.
Yeah.
And it was one space dimensional.
Well, my question was caused by the notation.
It depends. It's also possible to understand that this is a second derivative. But it's also possible. Okay. And so what we get, this is the main result, and we have proved that on gamma star, so ut is continuous and ut is bounded on gamma star in both cases. And now let's consider.
May I ask a question here? So
Yes.
that gamma, what was gamma what?
Gamma vertical.
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 So you have to stay away from that in order to prove Lipschitz and C11?
I'm proof here to I'm stay away from this gamma vertical in order to prove quadratical gross estimates.
Yes, but is that really necessary? Or?
Yes, it's really necessary because if you prove quadratic gross estimate, you should involve this Caffarelli monotonicity formula. And it's necessary to have subcoloricity from the first derivative
Yeah, but it's necessary for your method.
for method. But you see,
But do you know whether that is?
No.
You don't know.
Henrik, if you know how to prove quadratic gross estimate
don't
not
have
without contradictory arguments, then so it's crucial for this technique. Okay.
Do you expect something like C11?
So it's exactly C11, but up to the distance.
No, I mean, the expectation is to have like globally.
Globally, it can be some points where we have singularities.
What kind of thing?
What kind?
First thing you expect.
So it can be quite bad. So few minutes. So if we now move, so let's consider gamma 0. Contrary to gamma star, gamma 0, on gamma 0, time derivative can be unbounded. So we may have singularities. What kind it can be on gamma 0? So it can be something like this. Here, we have almost cusp here.
Can't you have that gamma 0 is part of, has some distance? The point of gamma 0 might have some distance to gamma b.
Yeah, yes. So, but Haik asked me about expected regularity.
This is what? This is
That's here. we may have something quite bad.
I see the picture is singular, but I don't understand what is it for. I mean, this is what? You? No, it's not you, right?
It's not you, it's a free boundary, and the singular point we may have here
For free boundary.
for free boundary.
Oh, okay, it's the time, space.
It's time-space picture. So time
On one
derivative,
side you have
time
the
derivative may be unbounded, so it can grow quite fast on gamma zero.
Around this, over this gamma v, the function is continuous, right? And it's like what?
It is continuous and continuous gradient.
Okay,
But
so
time
it's continuous.
derivative,
And time derivative is also bounded, but to the ends of this vertical.
Yes.
It may be single.
Oh, okay.
but from the structure, from the history of this problem, it should be not regular in that point. Otherwise, it would be not physical. Okay. So, and on gamma zero, what we have? On gamma zero, we have gradient u is 0. So no implicit function theorem. And here, a crucial step is the quadratic growth estimates. So what we prove for gamma zero? For gamma zero, we prove the following. It's the second lemma. So again, let's that 0 would be a point of gamma 0. Again, with some positive distance, I mean parabolic distance, up to the vertical parts. Then we have the following estimates. That oscillation of u over, let's show such, it would be less or equal and supremum of the gradient it would be true for all radius which are less or equal this distance. And this cylinder, it would be double parabolic cylinder. So I mean it would be in above and below. And how we prove it? We prove it first in the cylinder below using contradictory arguments. And here exactly we have a point that that 0 should not be element of gamma vertical. Since on gamma vertical we couldn't get that the positive of negative part of these functions are subcaloric. No subcaloricity, no Caffarelli monotonicity formula, no contradiction. So by this reason it's, and since we have the estimate in the cylinder below, then just apply the barrier arguments and get this estimate on the upper half of this cylinder.
But you have a very good geometry, you know, it's just a plane like this. Would that be used somehow?
You mean the geometry of what?
Are you saying this is just
Vertical parts?
so
No,
very
no, no. You see,
clear geometry?
that's nobody tell us it can be something like this. This geometry is good, and what to do if these points just come
So which one is omega plus, which one is omega minus here?
Okay, it depends on what we consider. So it's gamma alpha
You take
0.
it both
So
of them. You take it both of them. Possibly.
yeah, so it's I see. So
You don't know anything about how fast it goes?
Yeah,
This is
yeah,
in
yeah.
time,
yes,
yes?
yes, this is in time.
You don't know how fast it goes?
No, no. In fact, we tried to do this, but unsuccessful. But we have also no counterexample. So, but it looks like so. Good. And what we can do after that? Just remove this. And having this quadratic growth estimate, we can estimate first the time derivative. So what exactly we have? We just consider a point z0, which is on the distance on the vertical part of the boundary. We take this point and we claim that the time derivative at this point is just can be estimated via average integral and average integral of the which set. So let's consider this cylinder, low cylinder, with a center of point z0. And we start for some small radius, which is less than distance to the vertical part. And then we blow up this cylinder, unless we have met gamma 0. If we've met it, then we stop. Okay, say let it would be some parameter rho star, and consider a half cylinder. So in this cylinder, we are away from the vertical part of the free boundary and from the gamma 0. Generally speaking, gamma star is possible here. But, okay, and here we have the integral. So, and we can estimate this average integral using our quadratic growth estimates. So how we do this? So I write something which is not possible. It's on the right-hand side. In fact, instead of this, we should write some integral identity and then estimate all necessary parts. And then we arrive for the estimates for this average integral. Okay, so we have such an estimate. And the next step, we just show that can be estimated with a constant depending on m and the distance of this vertical part of the boundary. So we can estimate the time derivative. 1/2 of our theorem is proved. It remains to estimate the second order derivative. we can also estimate with this constant. So we have estimate of the time derivative. So the arguments is more or less the standard. So we choose a point, consider all directions which are orthogonal gradient at this point, get estimate for such derivative using Caffarelli monotonicity formula, and for the last derivative, so pure normal second order derivative, we can use our equation. So all mixed derivatives are estimated using Caffarelli monotonicity formula. Time derivative we have estimated. So it's, and we are done here. And the general scheme is the following. So, and we need, first we estimate derivatives, time derivative from gamma star, then quadratic growth estimates, and with quadratic growth estimates in hand, we estimate first the time derivative and then the second order derivatives. Okay, and I have at least 7 minutes. Maybe I just show you some part which, so this one-sided estimates on gamma star, since other part are,
What do you know about gamma in the neighborhood of such a point?
you mean, what do you mean?
What do you know about gamma in the neighborhood of such a point?
Which such a point?
The point in gamma 0 which is away from the vertical part.
Which is
The free boundary regularity.
free boundary regularity.
When you're away from
It's work in progress, so it's the next step. So you see, for gamma, also we are on the distance on gamma vertical. Gamma vertical itself is regular. Gamma star is regular. So in fact, here on gamma 0, we may have some kind of branch points. So we may have.
What do you mean by branch points here? I mean, it's a graph with respect to t.
Yes.
I guess it's not clear what it looks like near this point.
But it's, how to say, it's some, it's z0, and this is gamma 0. And things happen,
You can have
all can
branch
happen.
points. You can have, even without hysteresis, you can have branch points.
What do you mean by branch points
It
here?
means that there's omega plus, if you just look in the space, there could be omega plus, omega
Omega
minus,
minus.
Okay, but if
and
you
that's
say-
zero set.
But I guess one you would want
Then
to
here we have
Exactly.
no zero sets, Henry. Here no zero sets, no alpha set, no.
Okay, yeah, sorry. But I was thinking of the simple case when alpha and beta are equal.
Yes, but it's still in this case there is no sixth set of u equal alpha.
You should have branch
Prove that it's possible to make blow up this estimates, standard blow up.
So
If any zero
Yes,
point
and-
gradient vanishes, then we can describe all possible blow ups. It is
next it would be
flat.
sad.
even if
Such would
flat
be
t
okay and
equals
such would be
constant,
quite bad.
or
So just
flat
these two
t
cases,
x,
yes.
In x
Yeah,
space.
okay.
And having this, we try to prove the smoothness of free boundary outside vertical part, but we don't have such a result.
Yes, it's still in progress. So it's, in fact, these are fresh.
So the blow-ups,
Blow-ups,
one-dimensional?
No,
no,
many
many dimensional, but looks like this. Strange. Okay, and maybe I just show first how it's possible to prove one-sided estimate near gamma star of the time, one-sided estimate of the time derivative. So suppose that we have gamma beta star here. So that means that below we have omega minus. Here we have omega plus. And I would like to show that supremum of the time derivative. I take some point in the neighborhood of can be bounded from the one side with such a constant. And that zero, it can be arbitrary point near gamma star. So let's consider such a cylinder. Okay, how we can do this? Of course, it was again this forbidden idea, just consider equation for time derivative. We can do this instead of such an equation. We consider the integral identity. And integral identity we may write for the following construction. Here is a difference quotient from u with respect to time, its time derivative, some test function eta, again such a difference quotient, and this equal difference quotient of f and eta. And let's see, so how we define this difference quotient. This is a difference quotient with respect to time. So this means that x and from x and t. And we choose a test function eta as the following difference, time part of functions which depends on x and t. And let's see what we can say about this difference quotient. If we are here in omega minus, this difference quotient is 0. If we are above in omega plus, it's again 0. What's happened if we just go across gamma star? Here plus 1, here minus 1. So that means that this construction is always non-negative near gamma beta star. And we choose our test function in such way that it's also non-negative. So I can conclude that I have such inequality. And after that, so what we get here? Here we get the following. I'll rewrite a little bit. U time t, difference quotient plus x square plus and this is non-negative. And other activity is rather standard. So that means that we just preserve trivial and non-negative term on the left-hand side, rest send on the right-hand side, and estimate with the Young inequalities. So that means that we end up with the following. So we have integral here and supremum for all t plus integral and is a less or equal, something which we send on the right hand side. And here it would be some constant and such inequality would be true for all k bigger or equal 0. But after that, we immediately get the estimate. So what we can do, we can go to the limit for this radius of the difference quotient and get such an equality for the time derivative. And after that, we can write that the time derivative at points at 0, it would be less or equal as square root average integral from the quadrat of the time derivative. But if you remember, u is from w to 1q, so we can estimate it in some proper way. We have average integral, so we get here that the time derivative can be estimated for some constant, which would be just depend on the maximum of our solution. Какую? Перечеркнутую. В этом случае нет, я на гамма со звездочкой, потому что там у меня работает этот самый. Там работает.
But doesn't that depend on the distance? Or
No, it's not depend. This not depend on the distance. On gamma star, it does not depend on the distance.
that's not enough to get that. I don't understand. Because W1Q in T is not enough to get that. That's not.
No, it's
So then we just
ut.
Okay.
So it's
For our Q.
for a cube.
Kind of inequalities.
So let's say let's take the good scenario. U is C alpha in time. Why is that interval unbounded? Because you're taking mean value.
That's mean value. Ut is continuous across this part.
Aha, okay. So you're not using that.
Yes, no, not this. So ut is continuous. Yes, no, not here. No, not here. Not here. Not this point. No. Ut is continuous across this, so we estimate it, and then the average integral. Are you satisfied? Okay. So thank you very much. That's all.
Other remarks, questions? Not, let's thank Daria again.